Okay. So I hope I'm audible, and so I welcome you all to the problem solving session for the Introduction to Fluid Mechanics course. Uh, just to reiterate, uh, this course is taken by Professor Suman Chakraborty of IIT Kharagpur, and I'm Abhishek. I will be I'm the TA for this course, so I will be taking problem solving sessions for this course for 12 weeks. So this is the week 1 of the problem solving session. So just to confirm, I hope I'm audible. You can just say yes, no, or give a thumbs up in the. Okay,
Yes,
okay.
sir.
Thank you so much. So yeah, thank you. So I think I'll wait for 2 more minutes to start, but meanwhile I can just I think uh, continue with the introductory part of this session. So just to let you know, in these sessions I will not be uh, discussing too much regarding I will not discuss entirety of the things that were taken by Professor Chakraborty in the lectures. Like you might be seeing something that is on the screen, but these are just the gist of what is being taken by Professor Chakraborty in the lectures. So I will just go through the concepts like in a like go through the concepts slightly. Like I will just get an overview of the concept that were taught. Of course, if there is a doubt, you are welcome to ask. I will very much appreciate that. But I think it is understandable that we cannot expect that I am going to teach each and everything that was taken by Professor Chakraborty. So I am just going to revise it a bit, and then we will solve some problems that are relevant to the sessions taken by Professor Chakraborty. And the problem that I will be taking will be relevant to the type of assignment problem that you will be getting, and the questions that you might get in the examination. Okay. So I hope it is clear what will be the basic agenda for these problem solving sessions. So I hope that is clear. So if it is all right, then I think I can start now. And moreover, I expect that all of you have already attended the lectures that were in the course website. So I think all of you will be well versed with all of the things that I will discuss today. But if there is any doubt, you can ask. And then, as I mentioned, I will briefly go through the concept that we discussed for some time. So you may have to wait for a while before we start reaching the problem solving part. Okay, so if you feel that it is quite repetitive, you might leave for some time and rejoin again. Like it's your choice, but I will go through the concepts a bit. Okay, that's for sure. So I will not start the problem solving part right away. Okay, it's the regular agenda for all the problem solving sessions. So I hope you can understand. Okay. Okay, so with that, let us just start our discussion today. So I think, and yeah, for this course, this is again a undergraduate level course. So there is not much pre-requirement needed for understanding the course, but of course, as mentioned in the course website, a basic level of mathematics understanding is required, and I think all of you are well versed with that. So I won't even question that from my side, but then also the basic motivation for this course is to understand the basic fundamental fluid mechanics. Okay, so Professor Chakravarti might have started with a very nice session, introductory session that discussed about relevance of fluid mechanics in our day-to-day life. And I'm sure that all of you who are attending this course, like one way or another, are interested to understand the applicability of fluid mechanics on day-to-day life, and moreover try to understand the uh, understand fluid mechanics in a better way. So I think that is a motivation for all of you to attend this course. So as Professor Chakraborty might have mentioned, like it is fluid mechanics is everywhere, right? It's not only limited to liquids, but it's also relevant to air. And since air surrounds us all the time, so the relevance of fluid mechanics is insurmountable. Like it's very much relevant to everything that we encounter in our day-to-day life. Okay, so I hope this gives you a bit more interest to what we are going to do. And as mentioned by Professor Chakraborty, we will start with the basics, very basic concepts and definitions. So the first session today would be just relevant to that. Like we will discuss some of the basic concepts and definitions. But again, these are important because these are the foundations upon which we will build our further concepts, and all the mathematical derivations that we'll do, we'll build upon this concept that we discussed today. So if there's any doubt on the basic concepts, you might clear it out today. But these are the things that you might have to remember or recall throughout the course or throughout your life if you're dealing with fluid mechanics. Okay, so yeah, that's the importance of these basics. But again, since they are basics, these are not difficult to understand, but the difficulty is in able to implement these basics while solving complex problems. So all the problems that you are going to deal with in the later part of the course, you have to start with this basic approach. Okay, you have to keep the basics correct. Okay, and I think that's the what to say, foundation of all the courses, and the same is being applied to fluid mechanics as well. Okay, so let us start. So it's again a very basic definition here, a definition of 1 mole. It's an Avogadro's number of molecules in a particular lump of mass of, say, any matter. Okay, so if I say there is 1 mole of matter, it will mean that the number of molecules that are in that particular lump of matter is equal to the Avogadro's number, that is given by 6.022 into 10 to the minus 10 to the power 23 mole inverse. Okay, then for the basic fluid mechanics, so as Professor Chakraborty might have mentioned, like there are two basic approaches to understand or comprehend the subject of fluid mechanics. That is, first is the microscopic approach, and then the macroscopic approach. Okay, and both of these approaches are quite relevant and quite important. So if somebody says that one of these approaches is not important, it is entirely wrong. And I am sure Professor Chakraborty have mentioned that both of these approaches are correct and very much relevant to understanding the subject. But the choice of the approach boils down to what we are trying to achieve. Okay, so if you look to the microscopic approach, as the word itself might have let you know, that microscopic means we are looking into the fluid mechanics from a very small scale approach. Okay, we are looking or understanding fluid mechanics from its molecular approach. We are trying to look into each and every molecule of the fluid mechanics each and every molecules of the fluid, trying to understand how each and every molecule impart their force to anything that is encountering with or are in contact with, and understanding how these each and every molecule develop or flow in time. Okay, or move with time. Okay, so this is what microscopic approach basically means. Okay, and for example, Professor Chakraborty might have used the word pressure. Okay, he has used a word or definition of pressure from the macroscopic point of view. So if we try to understand the definition of pressure from a macroscopic point of view, it will basically mean the change in momentum of particles due to collision with other particles. Okay, so when we say the pressure is high, it basically means that there are more number of fluid molecules that are colliding. For example, if you are saying that on a surface there is more pressure. Okay, the surface is undergoing more pressure, so it will basically mean that the number of molecules that are over this surface are more. Okay, there are more number of fluid molecules or air molecules, you can say, for example, that are colliding on the surface of this plate, that is resulting in a higher pressure. Okay, and for microscopic point of view, it means that more number of particles are imparting their momentum on the surface of the plate, that is resulting in a higher pressure. Okay, so that's what macroscopic approach means. So of course this is correct, right? On a physical sense, on a basic physical point of view, this is correct, this is fundamentally correct. But the thing is, there is another way to understand it. Okay, Of course this is correct, but let us see what other way it teaches us. So the other way is the macroscopic approach. So the word again itself tells you that we are looking into the large scheme of thing, like what's the uh, overall effect of these collisions. Okay, so rather than, for I'll just draw the plate, I think that would be better. For example, this is the plate we're talking about, and there are initially say n number of molecules imparting their momentum on the plate. Okay, so if we were to look from the microscopic approach, we look into the force imparted by each and every molecule, say 1 2 3 4 4 5 6. We look upon the force imparted by these 6 molecules, for example, and see the net force that is being imparted by 6 molecules on the plate. That's what the macroscopic approach means. But for the macroscopic approach, it will mean that rather than looking into the 6 molecules, again 6 molecules is just a number that I have chosen, but it might be close to around say 2 3 moles, basically 2 times 6.02 to 10 to the power 23 molecules that are encountered by this plate. So again, tracking this number of particles and then finding the net force is a very tedious task. So that's correct, more accurate, but again extremely costly, extremely time consuming, and extremely computationally costly to do such kind of calculations. So it turns out that I think the other way, that is looking into the grand scheme of things, like the net effect or an average effect of all these molecules on the plate, would turn out to be a better approach. Like understanding, like for example, this is the given area I have. I know that there is a certain fluid, I know its mass. So let us try to define something like pressure to be the net force imparted by certain mass of fluid on a particular area. So this would be my macroscopic definition of pressure. Okay, so both of these definitions are correct. The the thing that boils down to the use of either of this approach is the cost effectiveness. Okay, so that's why these two approaches are important to understand, and is to understand the relevance. But again, for the rest of the course, or for the basic fluid mechanics course that we're going to deal with, we will stick with the macroscopic approach. Okay, we will keep our definitions, keep our derivations, and keep our understanding limited to the macroscopic approach. Okay, so I hope this is clear till now. Okay, yeah. So again we have just given you a definition, but we are dealing with fluid mechanics and engineering subject, so we need a parameter to, or a quantity to parameterize this particular definition. So the quantity that is used to define this kind of approach is given by the Knudsen number. Okay, that is given by Kn. Okay, so you will see that there are many such non-dimensional numbers that we will keep on defining in the course. For example, you will, a very popular non-dimensional number that you might know by now, like even before knowing the course, is Reynolds number. You might have heard it now and there. So this is again one of the non-dimensional numbers that we will eventually define. Okay, then there is Prandtl number. Okay, so these are some non-dimensional numbers that we would use to parameterize some of the quantities in fluid mechanics. So one of the first numbers that usually is introduced in a fluid mechanics course is the Knudsen number to quantify the continuum approach. Okay, so it is given by the ratio of lambda by L, where lambda is the mean free path of the particle. Okay, or molecular mean free path as defined by Prof. Chakraborty. It means that it is the average distance the molecule will travel before encountering any kind of collision. Okay, so that's the very definition of a molecular mean free path, and Knudsen number is given by lambda by L, where L is a characteristic length scale of the system that we are considering. For example, if we consider a pipe, I think this was again a definition example taken by Prof. Chakraborty. So if we consider a pipe, like out of common sense again, we can understand that the two length scales that might be of relevance is the length of the pipe and the diameter of the pipe. Okay, but since let me just tell you, since for most of the cases the length of the pipe is immaterial, in a sense that the pipes are usually very long or they are very large compared to the diameter of the pipe. So the main physics that occurs within the pipe is defined within the diameter. Okay, so that any kind of net change in the flow parameter that occurs would be relevant to the diameter of the pipe. Okay, that's why the characteristic length scale that we choose for a given system is again a choice of the person that is doing the analysis, but a common logic or a common, what to say, base that the fluid mechanics experts or the scientists have taken is to understand the length scale to be the length scale up to which, along which there is a considerable change in the flow parameters. And since the length of the pipe is too long to have any considerable change, like after say 10 or 20 meters, there is, of course, there is no much change in the flow parameters. So the only sensible parameter that we have where there is a change in say velocity or the pressure is the diameter of the pipe. Okay, so diameter of the pipe becomes the characteristic length scale, and this Knudsen number is, and here the characteristic length scale is given by L. So if this lambda by L is very small than 1, okay, it would mean that the system is very densely packed. Okay, so particles are very close to each other. That's why the mean molecular mean free part is very small compared to the characteristic length scale. So it basically implies the Knudsen number Kn is very small. Okay, and it is in this regime where the continuum hypothesis is valid. Okay, now again there is a other extreme end where the Knudsen number is very large than 1. Okay, so again Professor Chakraborty, when I mentioned it is then given by the very rarefied system where the particles of the fluid are very far away from each other. Okay, which is again even larger than the characteristic length scale of the flow. In these kind of systems, the continuum hypothesis is not valid, so we cannot usually implement our basic fluid mechanics equations to analyze such kind of systems. Okay, but again, for the scope of this course and most of the fluid mechanics course that we usually implement in engineering, in mechanical engineering or chemical engineering as per our civil engineering, we will limit our understanding to densely packed systems or systems where the continuum hypothesis is valid. And I think you know why the word continuum hypothesis is implemented, like why continuum hypothesis is required again. So you will see that eventually we will try to analyze the system using differential equations. Okay, which will again have some differentiation and integrations. So for this differentiation and integration to be valid, we need that the first and foremost thing we need that our function that we are defining has to be continuous, and thus the continuum hypothesis plays a role there. Okay, so I hope it is clear till now. Okay, so let us proceed. If there is any doubt, you can like I will like better would be if you just put your doubt in the chat box so that like the flow of the class is not hampered. But if you feel that there is some urgency and there's some point that you want to correct me during this entire session, you can of course unmute yourself and speak that doubt. That's also fine. But like for a general, what to say, for the better of the entire class, I think it would be better practice if you put your doubt in the chat. I will of course address it right away. Okay, so yeah, then there's the concept of system and control volume. Okay, and I think it is very important to understand the difference. So I think by now you have understood that which definition fits which approach. Okay, so there are two approaches as I mentioned, the Lagrangian sorry, the macroscopic approach and the macroscopic approach. So there are again two further definitions to understand the fluid mechanics problem. Okay, going through a control system approach or system as is written here, or the control volume approach. Okay, so as mentioned in the lectures, a control system would be a scenario where the mass and the identity of the fluid is fixed. Okay, for example, let us take again the case of a pipe itself, since we are repeating it. So I think going through a similar example throughout the class would be better for everyone. Okay, so it makes you to understand the same physics through different approaches. Okay, so that makes the concept much more clearer. Okay, so let us try to analyze a flow through pipe through a control system approach. So for example, now by now you have understood that control system approach would basically be aligned towards the uh, microscopic approach. Okay, for example, there is a flow through this pipe. Okay, this is the inlet, this is the outlet. Okay, and of course there are a large number of molecules of fluid that passes through the pipe. Okay, so as mentioned, as a control system would be of fixed mass and identity. So in this case, for the case of pipe, consider it we consider a single fluid molecule. Okay, say fluid molecule number 1. We are and we track this fluid molecule throughout its journey through the pipe. Okay, so it starts its motion here and then say moves throughout the pipe, going through, say the flow is turbulent, so it is going through random erratic motions and going out the pipe from here. Okay, at point B, this is at point A. So a control system approach would basically mean that tracking this each and every fluid molecule through the pipe and trying to evaluate the force that it imparts on the pipe at every time. Okay, at every time step. For example, if you are tracking the trajectory from say T to T1, then to T2, then to T3, and again you can choose the time step size according to your choice, but we'll evaluate the force imparted by the particle then at each and every time step, and then see the cumulative effect of this flow of this n number of molecules on the pipe. So that will give us the net force that acts on the pipe. Okay, that's one approach, and that is the control system approach. Why? Because first the mass was fixed, the mass of the chosen particle does not change. Okay, and the identity, and we are not changing the particle now. If we have chosen particle A, we are fixed with particle A, so the identity and the mass of the system has been kept fixed. That's why it is known as a control system approach. Okay, another example would be, say for example, if there is a container here and there is a fluid inside the container. Okay, in this case also, if even if you consider the entire bulk of the fluid here and try to analyze, say I will give you another perspective, say you are trying to do a thermodynamic analysis, like how temperature changes in this particular container of fluid. So in this case also, even if you consider the entire bulk of fluid, tell me, would it come under the control system approach or the control volume approach? Like if you're just considering this fixed particle, if this fixed mass of fluid, and then doing a thermodynamic analysis, like there's certain heat flux, there's certain work done, and that you're trying to find the net change in the say internal energy. Okay, I think I'm going a bit beyond the course, but just trying to understand if you're getting the concept correctly. So tell me, if you're trying to do this kind of analysis and the mass is fixed and the fluid is not going out, say again, imagine that the lid is closed. Okay, so there is no evaporation as per say. Now will this come under the control system? Can this be considered as a control system approach? Yes, no? You can try out. There's two options, right? Yes, no, either one of them. Like I will try to uh, help out if it is incorrect or correct. Simple yes or no. Okay, fine. It's completely all right. So again, in this case also, it will come under the paradigm of control system, primarily because why? This definition is important because see, the mass is not changing because there is no fluid going out of the container because of evaporation, because I've closed the lid, and the identity, and since it is not going out of the lid, the identity of the fluid molecules are remaining constant. So any kind of physical phenomenon that occurs within this fixed closed system can be treated as a control system approach. Okay, but as you can understand by now, like for the case of pipe, if we implement this control system approach for this n number of molecules, it is going to be it would create a havoc for all the scientists that are going to do this kind of analysis. So it becomes very very tedious and almost in most of the cases impractical. Okay, the result is or the outcome is too low compared to the vast computational resource that has been used to analyze the system. Of course it will be much more accurate, but again it's too much costly or too much time consuming compared to the result or output that we get. Okay, so to tackle that, there is another approach that is being devised to analyze these kind of systems, where there is a control, where there is a continuous flow of fluid through the system. Okay, that's a very important term. There is a continuous flow of fluid through the system. So in those kind of scenarios, we define a control volume approach. Okay, so again, this was again I think discussed, but let me just reiterate. So in the case of control volume, rather than tracking a single particle or say a mass of particle, we look or we keep our attention to a particular region. Okay, so for example, in the case of this pipe, say we are now keeping our focus to this particular cylindrical region. Okay, okay, say it is of say length small l. Okay, we are keeping our attention to this small region, and what we are saying that rather than focusing on each and every particle, let me just try to analyze the force imparted by the flow of fluid across this control volume. Okay, again this may sound a bit vague for now, like how we are going to evaluate these kind of forces, but again later in the course we'll see like there is a mathematical transformation popularly known as Reynolds transport theorem that helps us to evaluate or basically transform from the Lagrangian to the Eulerian approach and evaluate the forces, uh, the bulk force evaluated by the bulk forces imparted by the flow across this control volume. Okay, so as I mentioned, rather than following each and every particle, what we do is we keep our attention to a particular area or region and see how the flow of fluid through this region affects the net force or net pressure across this region. Okay, so that would be our different other method that we can choose. So in this case you will see that neither the mass or the identity remains fixed. Okay, because there is a continuous flow, and for example if the pipe is say expands, or I can say say if the pipe was contracting toward a region. Okay, then if there's a continuous flow, the mass may remain constant, but the identity will change definitely, because the particles that were initially there of will go out of the outlet, and there will be a continuous flow of particles through the region. So identity will definitely change. Mass may remain constant given that the pipe is of same diameter throughout the region, but the identity will definitely change. So in this case, this is known as the control volume approach. Okay, and these two approaches again come with another formal definitions known as the Lagrangian and the Eulerian approach. Okay, so Lagrangian will be correlated with control system approach, and the control volume approach would be correlated with the Eulerian approach. And for this course, we will keep our attention to the Eulerian approach and solve all the problems or try to understand the fluid mechanics subject using the Eulerian approach. Okay, so is it clear till now, or if there's any doubt you might ask? It's fine. I'll stop for say 2 minutes. If there's any doubt you can ask. Okay, so okay, it seems that if there's no doubt, I think we can proceed further. Again, these are very elementary definitions, given that all of you might already know it, but given the importance, I thought it's better to emphasize it on a bit. Okay, emphasize on it for a bit. Okay, So now let us look into the definition of fluid. So we have discussed about fluid a lot by now, but I think we have not formally defined what a fluid is. Okay, so again, depending on a subject and the interpreter, the definition of fluid might change. But for this course, and I think again Professor Chakraborty also agrees that it's a very nice definition. So he, in the lecture, he might have told that anything that flows is known as fluid. Again, he also mentioned it's not a bad definition, it's a very good definition and actually is in line with everything that we'll eventually discuss. But a formal way to define fluid would be that fluids are substances that undergo continuous deformation under the action of even a very small shear force. Okay, so he mentioned that if it would have been a solid rather than a fluid, and if we impart any kind of force on a solid, it will give us a reaction force, right? We will feel some kind of resistance uh, that would prevent the deformation of the solid, given that the given force lies below a threshold beyond which the solid may start to get deformed. Okay, so up to that point, when we are not able to provide that much of force, the solid will not deform. Okay, for example, if you have a pen with you in your hand, you try to give some kind of force, it won't deform unless and until it is so high that the pen eventually starts to break apart. Okay, but in the case of fluid, it's a very funny thing that even after the application of a very small amount of force, it will tend to deform continuously, and that continuous deformation is what that gives the flow like behavior. Okay, so that's the a very nice and formal definition of fluid, and this might be asked in your assignments or exams. Okay, there might be some the other definitions, but of course we will prefer, or the examiner will prefer, the definition that is being taught in the course. Okay, that is in line with everything that we are going to teach. So we will expect that you know this definition clearly. Okay. So yes, so then there was the discussion on non-deforming fluids. So again, if I go back here, let me go back here. So here, since the flow is continuously flowing, the fluid is continuously flowing, the flow is undergoing continuous deformation. But in this case, where the fluid is kept under a container, there is no deformation, right? The fluid is not flowing, so there is no kind of deformation. So these kind of scenarios where the fluid is not undergoing any kind of deformation is the scenario where the fluid is at rest. Okay, and you'll see that why this distinction is important. Like, what are the distinctions that may arise in the case of when the fluid is at rest or when the fluid is at motion. Okay, so you will see that eventually see that the types of forces that exist on fluid increases when the fluid is in motion. Okay, so you will see that eventually that shear forces come into picture when the flow is going where the fluid is going under motion. Okay, and shear forces are essentially absent in the case of stationary fluid. Okay, and for the next 2 to 3 lectures we will keep our attention to stationary fluids and try to understand what kind of forces that exist for the fluid at rest. Okay, so that would be our topic of discussion for the next 2 to 3 lectures. Okay, so as I already mentioned, when the fluid is not deforming, or basically if there is no flow, no shear force acts on the fluid. Okay, and I feel that you will know that what definition of a shear force means. Okay, what is shear force, what is normal force? I think these definitions you will know. Okay, so I expect that you know it already, so I won't emphasize it on it again. Okay, so when the fluid is at rest, there will be no shear force, but only normal force that would exist, and this normal force is essentially being termed as the pressure. Okay, so normal force per unit area in the case of a stationary fluid is known as pressure. But again, does it mean that if the fluid is at motion there is no pressure? It's a question, you can say yes or no. yes, no. Like, I think, of course, it seems that it sounds quite trivial or very, very like unimportant. I don't know, but I think if we want to make this session a bit more interactive and interesting, I think some kind of small question and answer in between would be good, would be highly appreciated. But if no, I think that's again fine, no problem. So, as I was mentioning, so I think again it is clearly discussed in the lectures that if the fluid is at motion, it does not mean that there is no pressure. Okay, pressure still exists, but additional forces will come into picture, which are known as the shear force. Okay, so to understand the pressure and the eventual discussion on shear forces, there is a again a formal definition that is required to understand these forces that acts on the fluid element. Okay, so in order to understand these kind of forces, we define what is known as a traction vector. Okay, it's, I think, for at least for this course, for the first 2 3 lectures, I think traction vector is something that is would be something that is not been discussed before this introductory fluid mechanics course. Okay, I think this is something new, so I think we can put some time on understanding this. Okay, so there was again a thorough discussion, I think 2 lectures almost, that was dedicated for the understanding of traction vector. So of course we don't have that much of luxury of time to discuss that thoroughly, but I'll try to capture whatever is important. Okay, so if there's any doubt, you might ask. Okay, so to understand that, we will consider the same example. We consider a small element of fluid, and again an outer element is also considered, just to make sure or make it look like the outer surface is exerting some kind of force on the inner surface, that is the red surface here. Okay, we consider a certain point on which a force, say df, is acting, a small force df is acting on a particular point. And the important thing to note is that the the traction vector that is being defined not only depends on the force F, which itself is a vector, which you might know by now, but it also depends on the orientation of the area at that particular point on which the force acts. Okay, so for example, initially the orientation is something like this, we will get a certain magnitude of traction vector. But say at the same point, if the orientation say changes something like this, the traction vector would change. Okay, and why this is important and how the orientation is taken into account is through the normal vector to that particular surface. Okay, so for this particular surface, the outer normal vector is defined by nk. So we say use that notation to take into account the importance of the orientation of the particular area. So again, if the orientation has changed like this, and say the it was defined by say n2, some other normal vector, then it would be given by t n2. Okay, so it is by that we like, it is by the normal vector of the particular area, we take into account the significance of the orientation of the area upon which the force acts, and thus the eventual definition of the traction vector. Okay, so as like from the mathematical point of view, or say magnitude wise, the traction vector would have a similar unit as pressure, because it's force by area, so it will turn out to be Newton per meter square. But the definition that's used to define it is a bit more complicated and advanced than a simple definition of pressure. Okay, so we look into it, why it is important and how we do it. Okay, just give me 1 minute. So as I already mentioned, the choice of the normal vector n cap as given here makes the traction vector unique. Okay, so traction vector is essentially used to find the components of stress in a particular direction, or the net effect of all the stress components along a particular direction can be what to say cumulatively represented through a traction vector. Okay, why? Because why it is important? Because see, in the case of fluid elements, as I already mentioned, it's not only the normal stresses, that is pressure that acts, but the shear stresses as well. So shear stresses will also impart some kind of effect on a net force that acts on a fluid element. That's why in order to take into account all these kind of forces along a particular direction, we take the help of the traction vector. Okay. So in order to understand it, let us take a cuboidal fluid element. Again, it's a very generic shape to make you understand, or I must say a simple shape that we're using so that you can understand how the components of the stress acts on this simple element. And once we develop the expression for this, the stress that acts on this particular fluid element, we can generalize it for any kind of shape. Okay, again you have to use some transformations eventually here and there, but you will get an idea that this is the way we can define the stress and eventually the traction vector. So but for that we need a base from where we can start our discussion. So we will start with a simple shape. Since a cubical shape or cuboidal shape aligns quite well with the direction of the Cartesian coordinate system, so we are using a cuboidal shape. Okay, so in order to understand that, let us denote the stress components. Okay, so by mathematical quantification, stress might also sound quite similar to pressure. Okay, but now as we dive deep into this course, we will see that stress is something, is a quite bit more advanced, or quite bit more what to say, or contains much more information compared to pressure. Okay, why? Because stress in general is a second order tensor. Okay, again, as mentioned by Prof. Chakraborty, we will not dive deep into the tensor analysis, which is, I think, beyond the scope of this course. But a simple definition, we need to understand that a first order tensor would basically be a scalar a vector which is given by, say, the normal vector n cap. And second order tensor would be a tensor that is defined by using two free indices. Okay, I might go a bit ahead and bit back here and there. So again, expecting that you already attended the lecture, so I think you will understand what the indices means. Okay, so I think I feel like I might have moved a bit further ahead. So, but still, let us try to come back and try to understand it more properly. Okay, so this is the cuboidal fluid element that we are considering, and consider a surface along the direction of the x component. Okay, so the stress direction of stress element, or the component of stress that acts along this direction, is given by tau 11, and tau is the symbol that we use to define stress. Okay, so we use now two indices to define this particular stress component. Okay, now you might say, why are we using two indices? Like why are you using tau 1? Why can't we just use 1? Okay, it's because both of these indices have their own significance. Okay, so the first index, that is the first one here, denotes the direction normal to the surface. Okay, so for this surface, the direction normal to this surface would be the stress component along the x direction, or x1 direction. So I will say that I will denote x as x1, y as x2, and z as x3. Okay, so 1 would denote direction along the x direction, 2 will denote direction along the y direction, 3 will denote direction along the z direction. Okay, so our normal vector lies along the x direction, so 1 will denote the direction along the x direction. The second index, which is 1 here, denotes the direction of the action of the force component. Okay, so since this stress component acts along the positive x direction, so the second index will also be 1. Differences arise when we look upon the other force components along this surface. Okay, so now by now you might have understood that this is actually the normal component, and these two are the shear components. Okay, So this will give rise to the shear stresses because it acts along the surface. So in this surface again, for this surface, for this component say, the first index will be same because the surface along with the normal rise is along the positive x direction. So the first index will remain same, but the second index will change. Why? Because the direction of the force that acts for this component is along the y direction. Similarly, for this component, the first index will remain same because the surface along which the stress lies or x, he has the direction normal along the positive x direction, right? So the first index will remain same, but the second index would change because it's along the positive z direction. Okay. So again, similarly, we take example of this case. Well, here the normal direction is along the y direction, so the first index will be 2 for all the components. The other components will change depending on the direction along which the force acts. So this will be tau 2 1 because it's 1, it acts on the x direction. This will be tau 2 2, which is the normal component for this case, the force along x along the y direction, and 2 3 here the force along x along the z direction. So let us take the example of the other case. Okay, the opposite cases, the opposite phase case. Okay, so in the case of opposite phase, again the direction normal will act along the negative x direction. Okay, but instead of putting something like -1 here, we compensate this negative sign or a change in the sign of direction normal by using a different sign convention for the direction of force. Okay, so if the direction normal is along the negative x direction, so the normal component of force that acts along this will be in the negative x direction as well. Okay, so both are in the negative direction, so our force orientation has compensated the negative sign on the normal vector. Similarly, we choose the direction of the force along the y direction to be opposite to that of what was there in the case of the positive n cap. Okay, so it is opposite to what it is denoted here. Similarly, we have chosen tau 1 3 in a way that it is the force the direction of force is opposite to that of the force that would have acted if the normal was along the positive x direction. Okay, so just tell me whether it is clear or not. Okay, I think, like, for me, I think that both in the lecture and my case also, I might have used, say, the definition might have been confused you a bit, but if it is alright, just let me know. If you want me to repeat, I will repeat it again. And if there's no comments, then I feel that it is clear. Okay, so yeah.
Hello.
Oh yes. Hello. Yes, yes.
Yes, it is a cube. If it is a cylinder,
Yeah.
then what are the fraction vector? Hello.
Yeah, yeah, traction
I'm
vector.
audible.
Yeah, you're audible. That, but
My,
yeah.
my question is if this is like for cube. My question is for cylinder.
Hmm.
So how we get the traction vector of along faces?
Okay, so again, let me just. So let me just try to put it in a way that, okay. So in this case, it is v1 v2 v3. Again, this definition for the indices will remain what to say same for the your cylindrical system as well. Only the uh, what to say the coordinates that are attached to these indices will change. For example, for the I'm not that sure, but let us try to look into it. So for Cartesian coordinate system, it will be something like x y z will denote the 1 2 3 indices. For cylindrical coordinate system, it will be again r theta z, which will correspond to 1 2 and 3. Okay, so In order to understand the stress components, again you have to, there is a very elaborative way to look into each of these coordinates. For example, if this is the cylindrical coordinate system, okay, sorry, I think this orientation would confuse you a bit, so let me just use the general one. Okay, so this will be your z coordinate, this will be your r coordinate, and how to denote it, this will be your theta coordinate. Okay, and all these coordinates are orthogonal to each other. Okay, so the corresponding stress components will look something like, say, tau r r, tau r theta, tau r z. Okay, so then again you have to choose some fluid element that is that would suit the cylindrical coordinate system, and again you have to do a similar analysis to find the stress components. Okay, I think I might not be able to do it right now, but the thing is, like, once you do it, like once you, like, see the definition that we eventually get for the stress components is like the traction vector, it is tau ji tau nj. It's in, like, you have to do a similar analysis to find the what to say, the traction vector for the cylindrical coordinate system. Okay, so I think for now I'm not able to derive it for now, but if you wait, then I think maybe we can discuss in the next class. But I think it will be in the similar lines. We have to draw the cylindrical element, the fluid element, and then carry out the similar analysis there. So I think it will be quite extensive one. So I am like quite not really sure how I will do that here. So is it alright if we discuss in the next class, if required?
It's okay, okay.
Okay, thank you. Okay, so yeah, again, this thought was quite like very welcome for this kind of discussions. But again, I think that for now, since I might not be able to clarify it again, this might require an extensive discussion, but these kind of doubts are always welcome. Okay, so if required, I think for the next class I will try to find the definition and try to give a very minimal discussion on it, and then maybe we can proceed forward. Okay, so yeah, again, so in this case, again, as he rightly pointed out, it is valid for your Cartesian coordinate system. So here we have three components along the I index, I1 2 3, and for similarly we have three components for J, that will be 1 2 3, this x y z direction. So eventually, if there are three coordinates, three independent coordinates, and three components along these coordinates, these independent coordinates, so we'll end up with, basically we'll end up with 9 components that are required to define the stress at a particular point. So by now you might have understood why this stress is far more advanced or far more informative than pressure. Okay, even if they have same units, basically in some scenarios they have the same usability, but the information that a stress tensor contains is far more advanced or far more what to say, more, it contains far more information than a basic pressure that is defined at a particular point. Okay, so in that similar line, let us I already discussed it, but let me just reiterate again. So in the case of, like, for scalars, we define scalar as a zero order tensor, so an vector as a tensor of order 1, and stress or these other higher tensors, like for example stress can be considered as a second order tensor. Okay, you will see that again the uh, deformation, the fluid deformation rate can again be represented as a second order tensor, so which we'll eventually see. But These are the basic definitions that you will need to know while we are discussing the advanced topics for this particular course. Okay. So now we just try to implement this traction vector analysis and try to find how we will be able to correlate this traction vector and the stress components that we have defined now. Okay, so again I will just take this similar route that was taken by Professor Chakraborty. I will take the same example, so I'll go through it once. If there is any doubt in this discussion, you might ask. Again, if there is any doubt beyond this discussion, also you are welcome to ask. But I like if they are quite advanced, I might not be able to discuss it. Of course, I might need some time to discuss it, but I'll try to clarify it if this doubt is relevant to the course in the next class. Okay, but if there's any doubt in this particular derivation or discussion, you are always welcome to ask. Okay, so Professor Chakraborty used this tetrahedron shape to derive a relation between the traction vector and the stress components. Okay, and he rightfully mentioned, oh, I think I have to charge it a bit, then I think I can like talk for a while, of course. So I may not be able to use the note for some while, but for some time, but let us try to, I will try to explain it by talking. Okay, so yes, the Professor Chakraborty mentioned that why he used this shape, primarily because in this tetrahedron shape, as you might see, three of the surfaces are special surfaces. Why? Because the surfaces say AOB, AOC, and OBC. These are surfaces that are along the special planes. There is the XY plane, XZ plane, and YZ plane, and these are special because the direction normal to these planes are along the direction of the this specified Cartesian coordinate directions. Okay, so it simplifies our analysis a lot. Okay, and the traction vector that we are trying to find is for the stress that is for the surface S that is not aligned with the any special coordinates. Okay, so we are using this shape so that we are able to simplify our analysis and define traction vector for a particular arbitrary surface that is S in this case. Okay, but again, as I mentioned, so this might not be the general case, so we might deal with different complicated surfaces. So but where we might need to again use a different analysis, of course. But for basic introductory course and basic introductory discussion, I think these kind of derivations will work quite fine. Okay, so that's why we start with this kind of scenarios where one of the surfaces are arbitrary, of course, but other surfaces are such that they are aligned with the special Cartesian coordinate directions that will help us to simplify our derivations. Okay, so I hope this is clear. So the normal vector for these special surfaces S1, S2, S3 are S3 S are given by N1 cap, N3 cap, and N2 cap respectively. Okay, because they are along the X, Y, Z coordinate directions. Okay, and the normal vector for the special surface S, in this case it is ABC, is given by N1 I cap, N2 J cap, N3 K cap. Okay, by this normal vector N cap. Okay, now we try to derive the Newton's second law of motion for this particular surface. Okay, because Newton's law is valid for fluids as well, which we'll eventually see. So we try to find the Newton's law of motion for this particular fluid element, and here we'll see how direction vector becomes relevant. Okay, so the forces that acts on the fluid any fluid element can be divided into two major forces or sub forces, that is the surface force and the body force. Okay, and we will see that it is the surface force that that needs the help of the traction vector to be defined completely. Okay, so to define the surface forces we use the traction vector. Okay, Okay, and for body forces we basically like define some parameters such as I would say the we defined body forces like some quantity per unit mass times the total mass of the fluid element. Okay, so that's why that's not that complicated to derive, but the surface forces, since the stress components that you will eventually see are basically related to the velocity gradients, so that's why the definition becomes a bit more complicated compared to the definition of the body forces. Okay, so I hope the difference between the surface and body force are understood. I think these are quite literal. Surface forces would mean the surface that forces that acts along the surface, and body force would be the force that acts throughout the body of the throughout the body of the fluid element. Okay, I hope this is clear. These are quite literal definitions, so I don't think there there should be any what to say doubt. Okay, so we have the from the Newton's second law. Let us try to first understand the Newton's second law for along the x direction. Okay, so net force would be mass times the acceleration along the x direction. Okay, so let B be the body force per unit mass. Again, as I mentioned, we define body force something like some quantity per unit mass times the mass of the fluid element. Okay, so now if I go back to the surface, I think the direction and notation of the stress components should not be confusing by now, so you can just have a look. I'm sorry that these are in the different pages, so this might be difficult to follow, but I think you can look into the kindly look into the definitions for a while, and then you will understand the derivation. Okay, so surface force affected by body force, no. Yeah, so yeah, thanks Gunjan for the doubt. So again, uh, see, let me just try to answer it in a way that that's the only correct way, but I don't know whether you will be able to grasp it or not. For example, body force, say gravity. Okay, in this case gravity. Okay, say, and again, yes, in general, yes, it will affect the surface forces. Why? Because say if gravity is the driving factor that drives your flow, so the velocity gradients or the velocity will be affected by the gravity. Okay, and since we'll eventually see that since the stress components or the shear stress components or even normal stresses that acts on the fluid are dependent on these velocity gradients, so and this velocity again is dependent on the body force that acts, in this case is gravity, then you can say that the body force might affect the surface force in a way, and this surface force and body force are coupled by the Navier-Stokes equation. Okay, the fluid momentum equation. So in that case, if you say that your body force affects the fluid velocity, okay, or the fluid motion, explicitly it affects the fluid motion, then of course it will affect the surface forces. Is this clear, Gunjan? Yes, thank you. Thank you. Yeah, thanks for the doubt. Again, it's a good doubt, but since we have not really formally defined the Navier-Stokes equation or the equation that puts both of them together into picture, I think it might be a bit difficult to visualize it now. But eventually, when we see the Reynolds-Sarsford theorem and the solutions to Navier-Stokes equation, you will see that what I'm saying, like how this might affect your surface forces. Okay, but that was a nice conceptual doubt. Thanks. Okay, so yes, so given that you already have attended lectures, of course, and you have seen the orientation of your what to say, the forces that acts along this particular tetrahedron shape, the net force that acts along the x direction or the force balance along the x direction is given by this equation. Okay, minus tau 11 s1 minus tau 21 s2 minus tau 31 s3 plus t1 n cap, the traction vector, times the area, because traction vector was what, force per unit area, of course considering the orientation and everything. So force would be traction vector times the area, right? Plus the net body force, this is the net volume of the fluid element, rho is density, and this will give you the mass times the body force per unit mass, and the net mass times acceleration is the ma term along the x direction. Okay, so now since I told that these surfaces are the special surfaces which align along the special directions of x, y, and z, so if you look into this surface, if I just go back, this surface ABC, okay, if you look into this surface ABC, this surface is basically the projection, or we can say that these special surfaces are basically the projection of this surface ABC on these respective planes. Okay, so you can define the surface S, of course by the help of unit the area vector for this particular surface S say S1 I cap, S2 j cap, S3 k cap, and the normal vector that we had, the general normal vector is n1 I cap, n2 j cap, n3 k cap. So if I want to find a component or a projection of the surface S along the particular plane, for example the xz plane, to the xz plane, xz plane, the normal vector would be the y coordinate, correct? So n2 cap will be the normal vector to the xz plane. So the projection of the surface S on the xz plane will basically be S dot n2 j cap, which is basically will be S2. Okay, so Sn2 will give you S2. So if I go back to the diagram, you will see that xz plane, the projection of S on the xz plane is basically S2. So S times n2 will basically give you the projection of the surface S on the surface whose normal vector is n2 cap. Okay, and similar analogies can be made for other surfaces as well. So if you substitute the value of S1, S2, S3 in terms of the product of surface S and the respective normal vectors, you can reduce this definition to this expression, like just substitute S1 in terms of Sn1, Sn2, and Sn3 respectively. So if you do that, you will get an expression of something like this. Okay, and again if you take one approximation further, like if you assume that the tetrahedron collapses to a particular point, or the height of the tetrahedron to approach 0, then if this h approaches 0, then these two terms will approach 0. Okay, this will be negligibly small. Then you can equate these stress components, the product of the stress components and normal vector, to the traction vector along the x direction, right? So we'll get T1n as tau 11 n1 plus tau 21 n2 plus tau 31 n3, correct? Okay, so as I mentioned, let me just, so as I mentioned, so in so this is, I hope this derivation is clear. Okay, so this would basically be the traction vector along the x direction. So it will be given by the stress components tau 11 times n1, stress component tau 21 times n2, and stress component tau 31 times n3. And if you look back, let me just again go back, I think that would be better idea. So we'll see that these are the stress components that acts along the okay, I think I should have, yeah, sorry. So if I draw something like here, I think that will be much more clearer. So yeah. If I draw another stress component here, so it will be something like, this would be tau 33, this would be tau 31, this would be tau 32, right, if I'm not wrong. So you will see that all these stress components, tau 11, tau 21, and tau 31, acts along the x direction, and it is the contribution of these stress components that are taken into account using the traction vector. Okay, and similarly along the y direction you will have components acting like, if you can say with me, tau 22, tau 12, and tau, oh, sorry, tau 32 actually. Okay, I think I have made a mistake here, so let me just, yes, tau 32. Let me just correct the diagram. I think this diagram is a bit incorrect. Okay, so it should be along the this surface, this surface along the this surface. Okay, so this would be tau 33, this would be tau 31, and this would be tau 32. So along the y direction the components would be tau 12, tau 22, and tau 32. Okay, similarly in z direction, tau 33, tau 23, and tau 13. Okay, so if you find the respective traction vector components along the direction, you will get the similar results. Okay, so I think now you will be able to deduce the other stress components as well. So what we see here is that we can now we can now replace this 1, like 1 with 2, then 3. It will give the components of traction vector along the other coordinate directions, right? So if we say replace this 1 by a independent vector or independent index such as I, so we can write this something like T1 Tin is equal to T1I N1 plus T2I N2 plus T3I N3. Okay, where I, if you change, you will get the respective component the traction vector. Okay, so if you want to again generalize it in a much more if you generalize it further, you can represent this traction vector in the form of this compact notation given by Tin would be equal to summation of j equal to 1 to 3 tau ji nj. Okay, where your j is the free index. Why? Because it is being repeated. So any index that repeats on a tensor notation, this type of notations are known as tensor notation because you are denoting the components using some indices. Okay, so these are tensor notation. So any kind of index that repeats in a particular tensor notation is known as a repeating index. Okay, or a dummy index. So this can again be compressed even further, where we can represent this as Tin is equal to tau ji nj, where summation is removed, understanding that the summation is over the repeating index j. Okay, and these kind of notations are known as Einstein's index notation. Okay, so as there was some doubt regarding the stress components for the cylindrical coordinate system, I think our analogy was similar. Like, I think that once you derive it, you will eventually boil down to similar expression where these indices will basically be changed by from x, y to r, theta, and z coordinates. Okay, the extensive derivation will require some diagrams, so I am not able to do that right now, but I think it will boil down to those notations. Okay, I was just a bit skeptical because there's a coupling between the theta component and the r component, which results in some additional terms, but let us just see once we derive it. But I think it will come down to a similar notation. Okay, I don't know if the person who asked that doubt is here or not, but if you are here, I think that will be we'll reach in a similar conclusion. Okay, yes. So is the notation clear? The traction vector relation between the traction vector and the stress components, the notation, is it clear? And I think the major takeaway from this would be the index notation, because eventually in the later part of the course we will again deal with this index notation once again, and I think that time I won't repeat it again. I would expect that you already know it, but if there's any doubt in the notation, you might ask now. Okay, or else we can proceed further. Okay, if there is no doubt, then I think we can proceed further. So this product, it is any doubt, you just check. Okay, So if this product, if you just again dissociate it and try to represent it in a matrix form, because see, this will give you a 3 cos 3 matrix, right? So you can basically understand it is a matrix multiplication. So the components of the traction vector T1n, T2n and T3n can be represented as a matrix multiplication between the stress tensor and the normal vector. Okay, so this times this will give you T1, this times this will give you T2, this times this will give you T3. Okay, so this representation is interesting because this basically tells you that a second order tensor, like basically we are trying to map the uh, we are trying to find relation between a vector, traction vector on the and the normal vector. Okay, so this relation can be obtained by mapping, by taking the aid of a second order tensor. So a second order tensor maps a vector on a vector. Okay, so eventually we'll see that for higher order tensors, a fourth order tensor might be used to map two second order tensors. Okay, which we'll eventually see when we discuss the Stokes hypothesis and this kind of, basically when we are discussing the Gauss transport theorem. Okay, so again, for sorry for the jargons, but just to give you a heads ahead. Okay, okay, so again we use consider a, again this is again discussed in the class, but let us just look into it. Okay, so we use, so instead of considering the cuboidal fluid element, again we just look at one of its faces, for example. Okay, say from the, we consider top view. Okay, for example, so from the front view, so if we take that projection, only the surface, we consider a 2D surface. Okay, then this will be the stress components that act on the surface. So are these stress components correct or not? I think I can leave you it as an exercise. Okay, you can after this today's session, maybe you can go and try to derive it yourselves whether this direction of the stress components are correct or not. But what I would say, these are absolutely correct. Okay, but it's for you to check it. You can try and check it. Okay, it will be a good exercise. So basically what we do is this example is used to find the symmetricity between the stress components, like whether tau 1 2 is equal to tau 2 1 or not, whether these are symmetric or not. Okay, so this example was chosen by Professor Chakraborty to find the symmetric nature of the stress tensor. So what we do is, for this 2D component, let us try to find the net moment. Okay, that acts on the particular fluid element. So tau 1, this stress component, okay, tau 1 2 will create a deformation or try to rotate this element along this direction, right, considering this as a positive direction, and the distance between this component and the origin is, say, uh, oh yeah, so say delta x by 2, right? So delta x by 2, correct? So I have just removed the 2, like again you can keep it, I guess that would be much better to avoid any kind of confusion. So say it is divided by 2 divided by 2. Okay, but it is the force that creates the moment, right? So we have to consider the force. So how we calculate the force? Force would be the stress component times the area on which it acts. Okay, considering the, say, the width of this surface to be 1. Okay, considering the width of this tube to be 1. Okay, just for simplicity, then surface area would be del y times 1, that is del y. Okay, so this is the force, and the perpendicular distance between the point of rotation would be delta x by 2. Similarly, this one, this component will try to rotate our element along the clockwise direction, which is opposite to this one. So we can take the clockwise direction to be of opposite sense to the counterclockwise direction. So that's why we take the negative sign, times the area, that is delta x, times distance, that would be delta y by 2. Okay, that would be equal to the net moment of inertia times the net uh, angular displacement. Okay, alpha in this case. Okay, so angular acceleration, if I'm not wrong, alpha, right? It's angular acceleration. So if you solve this and consider the approximation of delta x and delta y to be 0, then you will see that our derivations will boil down to tau 1 2 to be equal to tau 2 1. Okay, because this side will be equal to 0, and you can take delta x delta y to be common, right? Common from this, considering these are non-zero but very small, that's why it's approaching 0. So if that's the case, then we'll end down with tau 1 2 minus tau 2 1 equal to 0, or tau 1 2 equal to tau 2 1. But again, this derivation is valid up to a point where there is no body couple, right? There is no additional moments that acts on the surface. Okay, so given that, this derivation is satisfied, and in most of the cases you will see that in the absence of any body couples, which is the most general scenario in most of the cases, our stress components or the stress tensor is basically symmetric. That is, all the components such as tau 1 2 it would be equal to tau 2 1, tau 2 1, tau 1 3 would be equal to tau 3 1, and tau 2 3 would be equal to tau 3 2. Okay, so in general, given that there is no body couple acting on the fluid element, our stress tensor is a symmetric tensor. Okay, so yeah, I hope it is clear. So let us just proceed to the final part of today's discussion, that is a basic introduction to to pressure. Okay, so here we see that these components that have repeating indices, that is tau 1 1, tau 2 tau 3, these basically represent the normal stresses. So if you look back here in this diagram, this acts normal to the surface, and that's why are known as normal stresses, and these stresses acts along the surface, and they what to say, encourage shear deformation, that's why they are known as shear stresses. Okay, so in general, in a stress tensor, ideally there should be 9 unknowns in the stress tensor, but since stress tensor is symmetric, so in general we basically have 6 unknown components that we need to be needed to be found to completely define the stress in a particular point on a fluid element. Okay, so is there any doubt till now? We'll discuss, I think, for a few more minutes, 5 minutes like that, and then we'll start the Q&A part. So if there's any doubt till now, for up till now, you can ask, otherwise we can proceed. And just to, I don't know whether it is, I think it's already clear, but still, just to reiterate, most of the examples, hello sir, is it 3 normal and 6? Yeah, that's what I wanted to mention. Yeah, thanks for clarifying. So see, usually, as you rightly pointed out, there should be 6 components, 6 shear stress components, right? There will be tau 2 1, tau 3 2, and tau 3 1. Absolutely correct. In ideal case, total 9 components, 6 shear stresses and 3 normal stresses should be the unknowns in a shear stress tensor, right? But right away we have discussed that for most of the cases, tau ij is equal to tau ji. Okay, so like most of the cases in the fluid mechanics perspective, there is no body couple in the fluid element, so we assume or we take that for most of the cases the stress tensor is symmetric in nature. Okay, I think it will be better if I just draw the components. Okay, so it is tau 1 1, tau 2 1, tau 3 1, tau 2, sorry, tau 1 2, tau 2 2, tau 3 2, tau 1 3, tau 2 3, tau 3 3. Okay, so in general these are the 9 components of a stress tensor, correct? But since I told that tau ij is equal to tau ji, so it will mean that components such as this one and this one are equal, correct? This one and this one are equal, correct? And this are equal. Okay, so the only unknowns that basically we will have is tau 1 1, tau 2 2, tau 3 3, tau 3 1, tau 3 2, and tau 1 2. okay, because this would be equal to tau 1 tau 13, this would be equal to tau 23, this would be equal to, sorry, tau 21. Okay, so for symmetric stress tensor we will have six unknown stress components because it is symmetric in nature. Okay, so does it clear the doubt? Yes. Okay, thank you. Okay, yeah, thank you. Yeah, thank you so much for the discussions. Okay, so yeah, so as I was mentioning, like you might feel that all of this again for deriving pressure also, basically the Pascal's law in this case, again we are using a very simple diagram. Okay, so you might say that this may not be relevant to complicated scenarios. Okay, again well understood, but the thing is, to start a subject, to start and understand a basic concept of a subject, we have to start the basics, right? Basic scenarios from where we can implement the basic scientific laws, or basically what we say is starting from the fundamental law or basic principles that we already know. Okay, then to implement that and try to build upon that, we have to start with simple geometries, simple scenarios where these laws can be implemented. Okay, that's why we are using some very generic shapes, simple scenarios where the laws can be implemented, and basically we can find the components easily. Like if we sometimes say use these jagged kind of shapes, of course we can find it if required. We have to this jagged shape. Okay, say if you want to find the pressure on this case. Okay, so what we'll do is, of course it's very difficult to find a, say, the expression for the surface area for this kind of shape, right? We can't do it, so we have to zoom in very further, like this. Then we can say approximate it as a this kind of shape. Then using this, then we can find the components, something like that. Okay, so this is the way how I can say, like, the fundamental discussion that we are making can be, what to say, extended to complicated scenarios. But to understand this, we need to have the basic understanding, right? So that's why we are discussing all these derivations on simple shapes and scenarios, so that at least the fundamentals are clear. Okay, so yeah, again, just we let us complete our discussion with the basic introduction of pressure. So by now we might have understood that pressure is basically the normal stress that acts on the fluid. Okay, so and pressure acts in all the cases, whether the fluid is in motion or not. So even if the fluid is in motion, pressure will be there. Even if the fluid is at rest, pressure will be there. Okay, because normal stress components are sustained even in the case of even in the case where the fluid is not in motion. Okay, so for introductory sessions we need to understand, like, we start with the pressure, okay, as the primary force that acts on the fluid. Okay, so again we consider a very generic shape, this 2D shape, of course a 2D shape in this case, which is extruded to make 3D. Okay, to make 3D. Okay, so consider a generic surface along the x and y direction. Okay, so that our expression can be made simpler, of course, and a non-generic shape where we can find the components using the force components that acts along these generic surfaces. Okay, so that's the basic motivation for using this kind of shape. Okay, so we again use the Newton's second law. Okay, because this law is valid for almost everything that we encounter in our physical space. So we again, let us try to use Newton's second law to find the net force that acts on this particular surface. Okay, so the length or the dimension along the x direction is del x, along the y direction is del y, along the this generic shape is, say, L, length is L, and the length along the width of the, or the depth of this paper is, say, 1. Okay, so it is, say, 1, so that calculations are simplified. So the net force that acts along this surface would be Py pressure along the y direction times the area, that is delta x times 1, because the width of this shape along the depth of the paper is 1. Similarly, pressure at x along this surface delta y is px times delta y times 1. And similarly, the pressure at x along this surface would be the normal component of the pressure Pn times delta L times 1. Okay. So we need to find the force component that acts along the x direction, right? So we'll have this x along the negative x direction. So we will have minus px delta y. We will just disregard the 1 for now. Okay. Similarly, we will have this. This will not contribute any force along the x direction, so contribution from this is 0. But for this, it will have a component along the positive x direction, would be Pn times delta L sine theta, correct? But delta L sine theta, if you see, will basically be delta y. Okay, so see, L sine theta will be delta y, correct? So delta L sine theta is delta y. So we will have px delta y times pn delta y plus half delta x delta y rho bx, that is the net body force, because if it is the area of the triangle, then the volume would be this area times the width, right? It's 1 in this case. So area of this triangle will be half times base times height, half delta x delta y times rho, that is the volume, sorry, density times the body force per unit mass along the x direction. Similarly, this is the mass times the acceleration ax. Okay, so again you might ask, sir, we were discussing our fluid at rest, how the fluid is at motion here, why there is a component of ax? Again, let me say, the motion of fluid elements also considered. Okay, so the basic exercise for using this expression is to define the Pascal's law, that is pressure is transmitted equally along all directions for a fluid at rest. But one more thing to know is that this Pascal's law, that is the pressure being transmitted along all directions in a equally along all direction, is still valid for fluid at rigid body motion. Okay, so this something to know is that if we consider the fluid to move in a way where there is no relative motion between the layers of fluid, then we can consider a fluid to undergo a rigid body motion. Okay, the perfect example would be again the same example that we have considered. Okay, so if this is the closed container and it contains some fluid here, okay, and there is a pipe, flow through a pipe. Okay, so flow through a pipe. So in the case of flow through a pipe, you will see that, okay, since the fluid is in motion, of course the fluid moves, the bulk of fluid moves, but the key differentiating factor is that in this kind of motion there is a relative motion between the layers of fluid that basically gives rise to the velocity profile that we see. Or okay, if you are not well versed with that, if you have no idea regarding it, just take it for granted for now, for what I am saying, that for flow through pipes the fluid will undergo motion where there is a relative motion between the layers of fluid. Okay, but if you move this container with a certain velocity v, the fluid is at motion, correct? Because it is, the container is moving at a velocity v, but even though the fluid is moving, the fluid contained within the container does not have any relative motion between its layers. Okay, so even though the fluid is moving, there is no relative motion between the layers of the fluid. Okay, that's why, and this kind of motion, when there is no relative velocity between the layers of fluid in a fluid element or in a lump of fluid, we consider this kind of motion to be a rigid body motion. Okay, so we consider the acceleration of these kind of scenarios. Now again, if we consider the fluid element to be very very small, like if we consider this delta x and delta y to approach to 0, we will see that our expression will boil down to px to be equal to pn. Okay, this is what that we get force balance along the x direction. Now similarly, if we do the force balance along the y direction, we'll get Pn equal to Py, or if you again equate both of them, you'll see that you'll get Pn equal to Px equal to Py. So basically it states that the pressure is transmitted equally along all directions in the case of fluid at rest as well as fluid undergoing rigid body motion. Okay. So yeah, that's all. And there's one last definition, very small definition. I hope you will just discuss, just take it for what it is being said. Just take the definition. Okay, so there is one distinguish, or there is one like distinguishing factor between pressure. Like we consider two types of pressure. Like if we look at the very formal sense, we distinguish pressure into two parts: the mechanical pressure and the thermodynamic pressure. Okay, so mechanical pressure is basically determined by taking the average or a negative of the average of the normal stress that acts on the fluid element. And this definition is not only for fluid at rest, it is valid for fluid at motion as well. Okay, but when a fluid is at motion, we will take the normal stress of the stress tensor and take the average. Okay, so mechanical pressure is defined as the negative of the average of the normal stress of the fluid element. Okay, we will take the average, so divided by 3. Then again, there is thermodynamic pressure. So if you would have taken a thermodynamic course, or if you have a very slight idea, you know that pressure can be also be defined as, from a thermodynamic perspective, can be defined by the ideal gas law, or the equation of state, that is P equal to rho RT. Okay, so you might say whether these two are equal or not. Of course, these two are equal for most of the cases. Okay, but there are some rare scenarios, as mentioned by Prof. Chakraborty. There are some special cases where if the system under consideration undergoes very rapid changes, very rapid fluctuations. Okay, like if there is a forcing scenario, like for example, if there is a piston that moves up and down very rapidly. Okay, and this causes the fluid to undergo very rapid fluctuations, and if these kind of fluctuations are very rapid, then a fluid might not get enough time to adjust to these rapid changes, and in those kind of scenarios, mechanical pressure might not be equal to thermodynamic pressure. Okay, so these are the scenarios or distinctions where mechanical pressure may not be equal to thermodynamic pressure, but for most of the general cases, mechanical pressure is usually equal to the thermodynamic pressure. Okay, so I think that's all for today's discussion. So if there's any doubt till now, you can ask. Otherwise, we will directly go to the Q&A part. Okay, again, that's a very brief part because today's discussion is mainly some basic definitions and concepts, so there is not much of derivations or calculations that you might to do. But still, if there's any doubt, you might ask. Otherwise, I will proceed further. Okay, so if there's no doubt, again, if there's any doubt, you can ask. But I think we can start our discussion with the Q&A part. Okay, so I hope the screen is visible, the questions are visible. So again, you might feel that these are quite generic and quite repetitive, but these are the type of questions that you might get in your assignments. Okay, so kindly bear with me, and I assure you that questions will get a bit more complicated as the weeks proceed. Okay, but still. So for question 1, a fluid is a substance that A is practically incompressible, B always expands until it fills any container, cannot remain at rest under action of any shear force, or obeys Newton's law of viscosity. So which of the options are correct? Or I must say, which of the options are is the most appropriate for the definition of fluid? I feel that in many cases, all these definitions will fit quite perfectly for the definition of fluid. But as I mentioned, what would be the most apt option for the first question? You can write in the comments. Okay, D. Patrice says obeys Newton's law of viscosity. So okay, any other uh, opinions or answers, or should we stay with D? Okay, power says A. Okay, so Gunjan says C. Okay, so it seems that there are a lot of discrepancies, and as I told, this is expected because all these definitions are almost like applicable to the fluid, to a fluid in most of the cases. But as I mentioned, as an examiner for this particular course or a tutor for this particular course, I will expect an answer that fits the best to what we have discussed in the class. Okay, see, by this I am not saying that the other definitions are wrong or what I am teaching or Sir is teaching is the only correct option, but this is something that fits the best with the concept that we are trying to what to say impart to you for this particular session and the rest of the course. Okay, so keeping that in mind, if you recall, I mentioned that in the definition of fluid, fluid is a substance that goes under continuous deformation under application of a very small shear force. Okay, so if you go with that definition, option C turns out to fit it the best. Like it cannot remain at rest. So if it cannot remain at rest, it basically implies that it undergoes continuous deformation under the application of any shear force. Okay, is there any doubt? I think someone unmuted themselves. Okay, I think it's fine. Okay, so that's why option C is the most correct option for this particular scenario, but other options are not wrong as well. Okay, they are correct. So let me just give you one example for option A. Why it is not correct all the time? Because there might be scenarios where fluid may be appreciably compressible. Okay, so there is subject, separate subject known as compressible flow, where we see that fluid has a certain level of compressibility that like what to say, that generates some physics that are not usually visible in the case of incompressible regime. Okay, so by the definition itself, it says that there are regimes where fluid can be considered to be appreciably compressible. Second, it expands until it fills any container. Okay, again, it is also very correct, and sometimes is basically a superposition of this option C itself, but option C turns out to be a bit more, I must say, appropriate. Okay, for example, if you put a toothpaste, not say toothpaste, uh, if you draw a very very viscous fluid, say honey, or very, if you drop it in a container, like it will not like, fill the container right away. It will take a lot of time, correct? So again, in that way, it's not that like appropriate for this particular scenario. Obeyes Newton's viscosity. Again, there are scenarios where fluids may not follow Newton's law of viscosity, which we'll eventually see in the next class, I think, if I'm not wrong. So, but those are also fluids, right? So we cannot say that in all the fluids that only obeys Newton's law of viscosity are considered to be fluid. Okay, so again, that's not entirely correct. Okay, so thanks again. It's a very good what to say discussion. Let us proceed further. Okay, second option is, I think from now on I won't read the all the options thoroughly. These are too quite long, but you can read it and you can tell me the answer. Okay, choose the correct statement regarding the applicability of continuum hypothesis. Okay, so we discussed it in the beginning of today's class and discussed a Knudsen number. So, and I think this discusses about a regime or range up to which the continuum hypothesis should be valid. Okay, so again, it's a very simple question. You can tell the range up to which you feel that the continuum hypothesis would be valid. Okay, so Gunjan says option C. Any others? Do you have an opinion? D. Patrice says D. Okay, so let's say one more try. I'll wait for say one more minute. So again, thanks for the participation. And again, it seems that this answer again has to have certain subjectivity. Okay, certain level of subjectivity, because if I'm not wrong, the two options that for personally for me that felt quite similar were options B and C, because the range seemed quite similar. But again, is the most appropriate one, right? So in this case, again, the most appropriate one would be a scenario where the continuum hypothesis cannot be questioned in any way. Okay, so the best scenario for us would be a scenario where there is no gap between the particles, like the particles are almost connected to each other. So if that's the scenario, then the continuum hypothesis cannot be questioned in any ways, right? So the best way or best scenario would be to choose the value of Knudsen number that is at the smallest value, right? So option B, if you see, gives us the smallest range of Knudsen number, that is varying from 0 itself, 0 to 0.01, which basically tells us that there is almost no space between the fluid molecules. So in this case, continuum hypothesis will be very much valid, right? So that's why option B is the most suitable one. Okay, and option A and D are inappropriate because you can see that Knudsen number is almost reaching a value of 10, which is basically saying that particles are almost 10 times apart than the characteristic length scale. So that's why this option does not seem to be appropriate for implementing continuum hypothesis. Okay, I hope that answers your doubt. But B and C are both, I must say, acceptable, but option B is more suitable. Okay, because this is the concept regarding the continuum hypothesis is solid or not. Okay. Okay, thank you, Gunjan. So option 3, question 3. The number of components in a stress tensor defining a stress at a point in 3 dimensions is, I think it's quite simple. We just discussed it. So can you give me the answer? Yes, exactly. So it is 9. So I don't think there should be any. Yeah, thank you, Patrice. Thank you, Power. Thank you, Gunjan. So it is correct. So stress components, we saw that there are 9 components, right? So I don't think I have to reiterate again. So let us just not do it. Okay. So question number 4. Oh, sadly it is in 2 pages. So yeah, that I think it's still visible. Okay. Yeah. So question number 4 is, for a two-dimensional fluid element at rest, the components of the stress tensor can be represented as A, B, C and D. For a fluid element at rest, the stress tensor would be what? Option A, B, C and D. So you can start by questioning what would be the shear stress components for fluid element at rest. I think it's a very nice clue. C. Okay, Gunjan, Power, both of them say C. And like, if you recall that is correct, because if you see the diagonal elements, if you recall, should be non-zero. Okay, sorry, I'm not saying non-zero, are the ones that denote the uh, normal stress components. And since in the case of fluid element at rest, the shear stress components are 0, so other components will expect that they will be equal to 0. Okay, and the normal stress would be along diagonals, that is the pressure, only the pressure. Okay, some might say the diagonal components are these also. No, this is not correct. For a matrix, when we say that diagonal components, we consider to be this one. Okay, this is the orientation of the diagonal that we consider when we define the diagonal components. And moreover, leave the mathematical definition, like even when we look into the stress tensor itself, our diagonal elements are denoted here: tau 11, tau 22, tau 33. Okay, along this diagonal. Okay, so question number 5. So option number C is correct. Again, thank you, it was correct. Okay, so option number 5 is, the normal stress is the same in all directions at a point in a fluid only when a fluid is frictionless, only when the fluid is frictionless and incompressible, only when the fluid is incompressible. D, when the fluid is at rest regardless of its nature. So which is the correct? Gunjan says option D. Petri says option D. Okay, so it seems that the majority of you like are going or thinking towards the right direction, so it is correct. Okay, so we just discussed, like just before starting the problem solving part, we discussed that the Pascal's law, basically the pressure that is imparted along all directions equally in the case of a fluid being at rest or under rigid body motion. So we did not at all really emphasize on the fluid being compressible or incompressible, or whether it is friction or viscous or inviscid. Okay, so we did not look into this concept. We just started with a basic or very basic principles, saying that our fluid is at rest, okay, regardless of its nature. Okay, so that's why it is correct. So it is, I think it's very appreciable that you are able to grasp the concepts correctly, because most of the times it's very very simple, but sometimes people overcomplicate them. Okay, okay, so this is, I think, a bit tricky, so let us look into it. The bulk modulus of elasticity A has the dimensions of inverse of pressure. K increases with pressure, is larger when the fluid is more incompressible, and D is independent of pressure and viscosity. So I don't know whether you do, well, this is something related to solid mechanics. If you have taken solid mechanics course in class 11 and 12, at least in India, like we usually discuss about it. So let me just define it. So it is defined as defined by K, which is given by minus change in pressure delta P by delta V by P. Okay, so I thought that you might know, but since I didn't formally discuss it, so I wanted to reiterate it. Okay, okay, Gunjan says B. Very I would say nice like approach to the answer. So anyone else, would you like to contribute? So the important thing to note is that this numerator is not explicitly pressure. Okay, I'm saying change in pressure. Okay, so power says has dimension inverse of pressure. Okay, fine. Any other try? Okay, okay, Petrus also says A. So let me just okay, all are nice, but let me just try to reiterate. Okay, so we are discussing about the bulk modulus of elasticity. Okay, so it is defined as K. Okay, sometimes there is, I don't know whether I'm correct or not, but there is sometimes the definition of compressibility, like this given by 1 by K. Okay, but here I am explicitly discussing about bulk modulus of elasticity, which is K, and which is defined by delta P by delta V by V. So what would be its units? For delta P, it would be, say, pascals, right? Pressure unit is pascal, and delta V by V, since this is a ratio and both of them has the same unit, so it will be 1. So the units of bulk modulus velocity would be actually pascal, same as pressure. So option A is incorrect. Correct? Yes, thank Gunjan. So option A is incorrect. Okay, the other option that seemed quite reasonable, I think it was Gunjan, right? Gunjan pointed out that it might increase with pressure. Okay, so I think, yeah, it's going in the right approach. We're looking into the mathematical, you're directly attacking the mathematical perspective. That's correct. But the thing is, it's not explicitly the increase in pressure that we are considering. It's actually a change in pressure. Okay, so actually we define it as something like P1 minus P2. So if you say that, say the final pressure is increased or final pressure increases or the change in pressure increases, then this is correct, absolutely correct. But if you say increase in pressure, so it might happen that both P1 and P2 might increase simultaneously. Okay, so it says, see, this is science. Okay, we cannot leave anything to subjectivity. We have to be very very precise in our discussions. So when we say increase in pressure, I don't know in general whether it is only P1 is increasing or P2 is increasing or both of them are increasing. Okay, so if both of them are increasing, then delta P remains ideally constant, right? It does not change. Okay, so from that perspective, this option is, I won't say absolutely incorrect, but it's not suitable. Okay, and option D is incorrect. Why? Because compressibility explicitly is now depending on pressure, right? So we cannot say it is independent of pressure, even though it is in change in pressure, but it depends on pressure. So we cannot say it is not independent of pressure. So by elimination itself, it says that option C is correct. But again, I am teaching you the course, so I cannot leave you with this elimination option. Okay. So the way to look into is that, say K is delta P by minus delta V by V. So for a certain change in pressure, okay, for example, if the fluid is in a pressure chamber and if increase the pressure, okay, and say V is the total volume of the fluid, okay, V or initial volume of the fluid, okay. So if for a certain change in pressure, if delta V is large, okay, if delta V is large, it will mean that the fluid is more compressible, right? So better way to write it is something like V delta P by V delta P by delta V. Okay. So let us, this is constant, this is constant, considering that we are looking into the compressibility of fluid for a certain change in pressure. So if delta V is large, it will basically imply that the fluid is more compressible. So K will go down, correct? If denominator is large, then K will go down, right? But if delta V is small, very very small, like even though we change the pressure, the fluid is not like it's not compressing at all, like the change in volume is very very less. Then if this is small, this will go up, right? Denominator is small, then numerator will go up, correct? I hope you are getting it. So that's why option C is correct, because K will be larger if the fluid is more incompressible. Okay. So can you tell me, just from a mathematical perspective, yes, what would from mathematical, what would be the bulk modulus velocity for a completely incompressible fluid? For a perfectly incompressible fluid, which is usually not the case, what would be the bulk modulus of velocity? If yes, exactly. So in other words, we can say it approaches infinity. Okay, because delta V tends to 0 for a perfectly incompressible fluid. So this will, yeah, exactly, this will approach infinity. So K will approach infinity or will equal to infinity for a perfectly incompressible fluid. Okay, I hope this clears the doubt. So the final question is question number 7. Again, I will leave this to you. It's very simple. The first numerical another problem for this course. Okay, when the pressure is of a liquid is increased from 2 megapascal to 5 megapascal, the corresponding decrease the course thank you power the corresponding decrease in the volume is found to be 0.1%. The bulk modulus velocity for of the fluid K is given by, okay, so power is already given the answer. So I would say I will expect one more student to tell me the answer, then I think we can call it a day for today. Okay, so one more student can just try to solve it. So it's basically substitute the numerical values here. It will be minus V delta P by delta V. So I think the better way to put it would be delta V by V, because you are given the percentage change in the volume. Okay, just check the units. So it is increased from 5 to 2 to 5 megapascal. So delta P is 3 into 10 to the power 3 kilopascal, say, and this is 0.1%. Okay, or 0.1 divided by 100, that would be 3 into 10 to the power 3 by 0.001. So what will be the answer? I think I did all the calculation myself only, but See there, I have kept in kilopascal, that is kilonewton per meter square. So if you do it, sorry for rushing because time is already up, it will come out to be 3 into 10 to the power 6 kilonewton per meter square. I'm sorry, units we have to be very clear, right? It's number C. Okay. So is it alright? Okay then, time is actually up, but again, uh, thank you for attending today's session. Yeah, thanks Power. Thank you for attending today's session. Yeah, I'll try to clarify that doubt regarding the stress tensor, sorry, traction vector for this one cylindrical coordinate system. Of course I won't do the derivation, but at least I'll try to find the expression. But you might also try to look into it in the internet, maybe you will get an idea. But let us see, if this is a general doubt, I will try to clarify it in the next class. But again, thank you everyone for attending today's session. I hope it was quite helpful. Let us all meet next week. Okay. Yeah, thank you Gunjan. Yeah, okay then, I will end the class. Thank you Patrice.